My name is Nyal McCrea, by the way. I go to Central Washington University in Washington State, 2 hours outside of Seattle. I just want to give a thanks to my mentors real quick, Ethan Nadler and Vera Glusevich from USC. They did a great job mentoring me through this process. And so, yeah, let's get underway. So first off, I'm going to give you guys a little background on what dark matter is. So scientists believe that it's 84% of the matter in the universe. With that being said, everything I'm going to tell you today is still just a hypothesis. We actually don't know if it's out there, but there's strong empirical evidence from gravitational interactions between barons, so subatomic particles, and itself, so in-body interactions. So how dark matter forms, it forms in these things called halos, which is over here. And disclaimer at the bottom, you actually can't see it. It's black, but for a representation, we colored it in just to make sure y'all could get a grasp on it. So yeah, it forms these things called halos. And if we go to the next slide, we can actually see how these halos are formed. So right here, we call this a merger tree. So what's going on in this picture is happening over here in this diagram, because we like our diagrams. Okay, so this is Z over here. This is our redshift. So as you can see, the redshift decreases over time until it hits 0. And we call this our interest area. So this is the Z shift we're interested in when we measure this. So basically what we're looking at is so there's two types of halos. There's host halos and there's subhalos. And so the subhalos can become part of the host halo by smashing into it. Even subhalos can have be host halos for their own subhalos. So as you can see, D is the host halo for A. And then they form, yeah, as I said, smashing these trees. Now, there's also another way that kind of dictates when a subhalo is going to become a host halo. And usually scientists believe that's at the virial radius. So as you can see, the colorness right here, this purple color, that pink color, the other pink color, and that just white color for that little a, those are all like the boundaries of the virial radius. And what happens when a subhalo enters that, it officially becomes part of the host halo. But due to tidal forces, it can actually be outside of that. So there's some host halos that actually are actually bigger than their virial radius. And if you want to move along, yeah, to the next slide. So what did I look at? I looked at hydrodynamic simulations. And in hydrodynamic simulations, we include baryons interacting with dark matter through gravity. So what are the effects of these interactions, gravitational interactions? Well, as you're going to see in the simulation, there's less of these subhalos moving inside the virial radius. That has a direct effect due from the barons. It's more of a spherical movement. So it's more circular throughout. And it moves in these things called short axis tube orbits. And there's actually gonna be a picture of that just about to coming up here in the next slide. So if you want to go to the next slide, you can actually see these orbits. Now, in my simulation, I'm doing a 2D simulation. So my simulation is in the XY plane. And so you can see it's gonna be more circular and more of a, I guess, symmetric kind of movement. Now, if we go to the next slide, we got our in-body simulation. Now, this right here is dark matter only. So dark matter is only interacting with itself. There's no barons in it. And it's self-gravitational system. And in both these systems, I guess not in the barons, but usually with dark matter, the thermal energies, it's negligible. So we really count for that. But so in this system, we just say there's no thermal equilibrium. There's a gravitational collapse, produce a power law density profile in the center. It's a more chaotic system, so more random kind of movements. There's a box and thin orbits. It's more of a triaxial system. So, you got your axes, you got your X, Y, and Z, so triaxial system. And it becomes more spherical over time. And it's a more oblate shape. So if you need to refresh your shapes, or if you just don't know them, I got them over here for y'all. Okay, so now we're gonna start our simulations. So if you want to go to the next slide. Oh yeah, these are the orbits we're looking for. So if you're gonna look for these orbits inside of your simulations, if you can find them. So if you want to go to the next slide, we're officially gonna start our simulations. So I just want to say we're starting off with the hydrodynamic simulation. So this is ones with baryons, subatomic particles. This simulation is done with a fire code. What a fire code does is it takes feedback from a realistic environment and then produces an outcome. What I did was I took that data and I made it into a plot, plotting our galaxy. So this is our universe, essentially. The red dot in the middle, that's our host halo. That's 0.22 megaparsecs. Oh, like wide. Up top, you have your subhalos. Then you got your scale factor, and over on the side, you got your redshift. So Z is your redshift. As you can see, it's decreasing throughout time. Now, what I did is I took 560 snapshots in PNG files. Originally, PDFs, we had problems with the alpha channel, so the transparency. We still did, no matter what. And we had to make it into, I just left it as a PNG. So this is a dark matter only simulation. As you're gonna see, there's gonna be way more. It's gonna be way more chaotic system. And again, the red dot in the center is our host halo. That gray area, that's our virial radius. So both simulations, that's our virial radius, and that's gonna grow over time because as you remember, as subhalos go into that virial radius, they add on to the host halo, making that virial radius even bigger. So up top, yeah, you can see it's still same scale factor, still the same redshift, and this is dark matter only. And you can tell there's way more dark matter halos. So yeah, if you wanna, I guess, move on to the next slide. I can talk about that for a minute. You guys wanna watch those again? Are you guys good? Okay, just checking. Okay, so as you can tell, there's, as I said before, there's less halos in the hydrodynamic simulation. There's this phenomenon called splashback, which was originally thought not to happen in these dark matter halos, but over time we found that it could happen. And that's what happens is when a dark matter halo enters the virial radius at some point in time, and later in time, it leaves the virial radius. And so we call that splashback. And another thing, as I talked about earlier, subhalos can orbit each other, right? Because it's the gravity interaction, so they can orbit each other also. So yeah, I guess the next slide, please. Oh, so conclusion. As I tell you before, these are different simulations, right? But also, they're simulating orbital mechanics, right? Like, if we come up with a theory, we want to see how it works in the nature, right? We don't just want to be like, well, we kind of think about it, We don't really know how it works. We actually want to know how it works. And using simulations like these can actually describe how it works. And humans, we're visual animals. Like, we like to see something. We like to see it work, right? So, next slide, please. So going forward, we can actually track each one of these subhalos using something called a Fourier spectra. What is a Fourier spectra? Well, it's basically a term with a complex exponential, right? So you're getting your sines, you're getting your cosines, and that kind of makes like orbital mechanics moving, and you can dictate like what kind of orbit you're gonna have, right? And then the most important thing is in that Fourier spectra, we get something called angular momentum. Angular momentum is dictating all those orbits we saw earlier. So in that angular momentum, there's 3 triplets. And depending on how those triplets are aligned, we get thin orbits, we get chaotic orbits, we get boxed orbits. We even get these things called resonance orbits or resonance frequencies, and they have their own orbits. And that's if one of them is 0. But we can use different dark matter simulations. So far, we theorize that there's 3 different kinds of dark matters. There's cold dark matter, there's warm dark matter, and there's self-interacting dark matter. The problem with the last 2 is they can't survive on a galactic level on a linear power spectrum. So what happens is the self-interacting dark matter, it dampens off like this. You know what happens to the warm dark matter? It just falls off. So we're left with this logarithmic cold dark matter going up. And that's what we think most of our universe is at this point. I forgot to mention those simulations. That started from the Big Bang. Each one of those snapshots you saw was 23 million years. So a lot of that could be cold dark matter. We still don't know because we're still in the hypothesis stage, but we're getting there step by step. So yeah, is there any questions for me on my talk?
mentioned in the simulations you were looking for these specific types of orbits that they look like a saddle, or I forget what you called them. Why were you looking for those?
You want to go to the next slide? Let's go. I'm so glad. These parameters right here, they come from experiments, right? We know that from like Q and stuff, initial conditions, right? Those initial conditions can come from big scale phenomena or really small scale phenomena, right? And those dictate these kind of orbits. If we know these orbits, we can get a better understanding of the experiments beforehand that dictate those, leading to a better conclusion of where dark matter comes from.
Okay.
In short.
Just one quick question. So the initial conditions for the simulations, the same total matter, dark matter versus baryonic matter. So
overall?
Yeah, overall. So what were the initial conditions for each of the?
So for the initial conditions for the baryonic ones, there's less dark matter because they're getting torn apart by gravity. But there's more. Oh, okay. Sorry.
The matter is not torn apart.
So sorry. At the beginning, there's the same amount of subhalos, so 0, because it's when the Big Bang started. As I said earlier, dark matter is thought to be relics from the Big Bang, thermal relics. It decoupled later and became just cold dark matter. That's one of the hypotheses. So in both the simulations, it's going to start off as 0. And then over time, more and more subhalos are going to come in. And depending on if it's baryonic, it's going to have less subhalos because the gravitational interactions are actually going to physically pull it apart from the baryons and the dark matter itself. And there's going to be more over time in the in-body or just the dark matter itself.